Hi everyone, Professor Gassimi here. In this component of the lecture, we're going to be speaking about statistical constituency parsing. Now, in the previous component, we learned how to use a context-free grammar with CKY to obtain the set of all possible ways that you could parse a sentence. So remember, we had an algorithm where we stepped sort of along each of the words in order, and we followed the rules of the grammar to give what the possible possible values of this token down here was. We started with the first order parts of speech tagging. We moved up one level then and said, hey, now, given that I have parts of speech tags available at this position, am I seeing any matches? And we noticed things like, for example, that we could call this a noun phrase because it was a determiner followed by a noun, okay, which existed, as you can see up here, in our grammar rules. Okay, and we kept doing this sort of moving up all the way until we got to the top level of what represents the parse tree, which was the final sentence. Okay, but ultimately we did this. Why? Because, as we've been discussing, there's more than one way to parse these sentences. And in this incredibly simple example, the word eats could be a verb or it could be a verb phrase. And so the question is, how would we know which of these is a more likely option so that we could parse it accordingly? Well, the simplest way to do this is to just account for the probabilistic nature of language that we've come to appreciate so far, all the way up to this point in the semester. That is to say, instead of taking a lexicon and a grammar, like what I'm showing here, we could convert this to assign probabilities of the words and the grammars using some training data, for example. And this is what's referred to as a probabilistic context-free grammar. Now, these probabilities would tell us the odds of a given constituency. For example, I've highlighted here in red that notice that we've got the same old rules that a nominal is either a nominal followed by a noun, or a nominal followed by a prepositional phrase, but these all sum to 1. So you could fairly ask the question, well, hey, where do I get these probabilities from? And the answer is you go to what's called a tree bank, which are large corpora that have been carefully annotated by folks who are very, very good at, extracting grammar from sentences. Think probably your grade school English teacher sat and annotated a bunch of documents to basically write out what the parse tree was. And so you can use that to sort of get prior probabilities about how often is a nominal a noun versus a nominal and a noun versus a nominal followed by a prepositional phrase if you had access to those parse trees in a training data sense. Okay, and similarly, if you had access to parts of speech tags in a similar kind of data set, a tree bank or some other source, you could say for any given part of speech, like a determiner, can I have the probability that these words show up? This is going to be particularly useful when you have multiple senses of a word, right? You might be able to, for instance, assign the fact that fat is more likely to exist here within the verb category, at least relative to the other verbs, than it would be within the noun category or whatever. Okay, but ultimately, the useful thing about having the probabilities in our context-free grammar and being able to enumerate the parse trees using CKY is we can use these to now compare the probabilities of alternative parse trees. So we could, for example, see that book the dinner flight has 2 different ways of being structured. It could either be a verb followed by a noun phrase. So a verb is book, and then the noun phrase is so book the dinner flight. Or it could be a verb, book, followed by a noun phrase, the dinner, so book the dinner, followed by another noun phrase, which is flight. And these are 2 possible ways to parse the sentences. Okay, and obviously this one seems, at least to me, more intuitive as it's a correct way to parse the sentence. Well, we can use the probabilities and the rules that we had described in the probabilistic context-free grammar so that we can figure out if that's actually the case. So we'd say, okay, well, what does this parse tree imply? It says that I have a sentence which is consisting of a verb phrase, and I could go back to the rules that we had specified and say, okay, the probability of that is 0.5. And then I could say, okay, now I have a verb phrase being consisting of a verb followed by a noun phrase, and the probability of that is 0.2. So I multiply these two probabilities. And I continue following this all the way down the tree, each time multiplying out the probabilities until I get a final very, very small probability. Obviously, if you're doing this in a machine, you would probably want to take a log sum of these probabilities to prevent numerical underflow. Just kind of giving you that as a hint for when you deal with these either on your own or for the homework assignment later. Now, the key thing here, though, is that because I had the probabilities, I'm able to assess the likelihood that this particular sentence, book the dinner flight, had the grammatical structure that was implied by this parse tree, right? That's the whole point of this. And I can do this for the other alternative. And what you can see is that the second alternative, where I had a verb followed by the noun phrase, the dinner, followed by a separate noun phrase, flight, is less likely. That is, the probability here was 2.2 times 10 to the minus 6, and here it's 6.1 times 10 to the minus 7. So that means that this is the less likely candidate. And so we would be able to identify the correct or most likely parsing tree using this approach. Now, probabilistic approaches to this basically can be kind of wrapped together with CKY to describe what's called probabilistic CKY, which effectively just gives you this maximum probability parse. And I think if you understood how the CKY algorithm iteratively goes about enumerating the possibilities, and you also understood how you can compute the probability of each of those possible sequences that are enumerated by CKY, then the implementation of this algorithm should be, with a little bit of work, my hope is pretty straightforward. Okay, I want to bring up, though, as we sort of close the conversation about statistical constituency parsing, that probabilistic context-free grammars have two deficiencies which make them incapable of modeling important structural and lexical dependencies. That is to say that they're not perfect. The two problems are there's an independence assumption, so they impose an independence assumption on the probabilities, and this leads to poor modeling of structural dependencies. What do I mean specifically here by an independence assumption on the probabilities? Well, remember, we were just kind of doing a straight out multiplication as we walk down the parse tree. But intuitively, we know that that's not correct. There's probably a transition or a conditional probability there that we should be accounting for. So the independence assumption here is naive. The second one is that there's no lexical conditioning. That is, we don't model any syntactic facts about the words. And this can lead to problems with subcategorization, ambiguities, and prepositional attachments. So what do I mean here specifically is that there's certain words that just those words in particular tend to show up and be used in particular grammatical contexts. And they're very, very likely to show up in very specific contexts. And this model doesn't have a way of accounting for those nuances. There is an extension of probabilistic context-free grammars called probabilistic lexicalized context-free grammars that solve these two problems. We won't be covering them in the lecture or in this course, but I wanted to bring it to your attention so that if this is an area that you're interested in working on or leveraging, you are at least familiar with a technique that solves these two weaknesses of the approach we've discussed.